Okay. Hello, and this is a kind of another explanation for the things that were covered in Chapter 7, looking at how we understand the atom to what it is today. And at the beginning, we talked about the history. I gave you guys a quick review about these guys, that they all contributed to a piece of the puzzle as to who they are, what they did, okay? Shout out to Ernie, okay? And then a shout out to Niels, because, you know, they did come up with some things. We talked a little bit about the review of the periodic table, but then we have to get to electromagnetic radiation and energy, because that's a huge thing. Right there. We have to look at a couple of things. Where light, well, it's an electromagnetic wave, but it also has some particle properties as well. Right now, today, there's a dual nature of light. But for now, we're going to look at the electromagnetic wave. We're going to look at the wave part. And we got the wavelength and the frequency. Well, if we look at it, wavelength and frequency, there's a definite relationship that's there. If this is the entire electromagnetic spectrum, we can look at waves in terms of how much energy and the frequency. Well, if the wavelength is the distance that the top of one wave to the next, and then we have to look at the frequency, and the frequency is how many of these waves pass a point in a second. And, well, wait a minute. That means they'd be traveling at roughly about the same speed. Yeah, because they're traveling about the speed of light, which is 186,000 miles per second, or about 3 times 10 to the 8 meters per second. Okay, give or take. If it changes from a vacuum of space into the atmosphere of the Earth, it actually slows down a little bit per se. So let's look at this. How does that relate? Well, if we're looking at the wavelength for the distance of one wave to the next, it's kind of like taking the clapping of the hands. We can have a very short wavelength or a very long wavelength. Now, if we can go ahead and actually simulate clapping our hands as fast as we can, not many waves have passed through. But on the other hand, a shorter wavelength, what did you get? You got more claps. Well, wait a minute, what do you mean by more claps? More waves passed in that time period. Now, which one do you think is going to have more energy? This or... Well, if you're doing this, and you picked this as having more energy than this, you picked this, you are right. That is, in fact, more waves. More energy, more waves pass by. Okay, that's nice. So we know that waves have to have energy in order to move around. Okay, so what happens? What's going on? Why are we seeing these colors? Well, here's the thing. The only way we get to deal with these different forms of electromagnetic radiation is we have to be able to pick it up. So energy has to either be absorbed, sucked up, or given off. How do the scientists know where the energy, do we detect it when it's being absorbed or given off? Well, the easier option is actually being given off. So when we talk about lines like these, we're actually saying, look, the electrons are coming down, they're coming off their higher point, and they're giving off this energy. The energy that they give off, we pick it up. We pick it up with these lines. Okay? What's going on? What do you mean about these lines that they're being picked up? They're called emission lines. Emission meaning you're giving off something. Okay, that's the key thing. You're giving off something. The only way we can detect these is that the electrons are in fact giving off energy and we're able to pick it up. Now you say, well, wait a minute, I don't get this. Well, the idea was this, that there were energy levels around the atom. That's what Bohr proposed. that there were energy levels around the atom, so electrons that were in the atom, they would go and absorb energy. If they absorb energy, then they would jump levels. Kind of like a kid, if you give a kid sugar, okay, in the form of cookies and a soft drink, like Coca-Cola, they're going to absorb that energy. That sugar is going to go into their system. Natural process, right? Well, it's kind of the same thing about electrons. When electrons absorb the energy, we're not really seeing it with the emission lines. We're not. Now, absorption, that's different. That I'm not going to worry about that. I'm going to look at the emission lines that we have. So what in the world are we saying? Well, if we look at the modern view, if we take a look at the modern view of the atom, where we have Heisenberg's uncertainty principle, the idea that we don't know where electrons are going to be at any one time, we can press a light. And light is made up of photons. These photons, think of them as packets of energy. Now they're going through and they're hitting these hydrogen atoms that are in this box. Now we can turn it off, and then that's it. So here's a hydrogen atom, and this blue area around here is dealing with that cloud, that quantum model, that region. I mentioned Ontario Mills to the class. Imagine one person being in Ontario Mills. That kind of gives you the idea of what's happening with the electron inside this region. Or you may want to look at it as take a marble and put it in the middle of the football field at the 50-yard line. And you have the surrounding of the football field. That gives you an idea that the size of the electron and how much space the electron has to move. And that's why we have to represent this blue here, because we don't know where the electron is going to be at any one time. We don't know what it's going to be doing. We don't know where it's going to be at any one time. And that was Heisenberg that came up with that. Okay? Now, here we got our simulation. We have our spectrometer here that's going to record our emission lines. Here, we're going to have our energy levels. Okay? So we have our electron here. Let's go ahead and let's get this thing going. We're going to turn it on, and now look what happened. What did you see? You saw the electron jumping up to a level here. And what did you notice happening here also? Notice how the blue went from that little tiny thing to boom. What happened? The electron absorbed the energy. Well, wait a minute, where did the energy came from? One of these packets of energy we call photons from the light. Why are there different colored packets of energy, these photons you're talking about? Because white light is made up of all these different colors. Wait, how do you know that? Rainbow. When it rains, the sunlight goes through the rainy parts and it breaks the light up into the different wavelengths of light. The color tells us the energy that that electron had. That's the key thing, the color. Now here, we can start looking down here. Notice, oh, you got some ultraviolet here. That's awesome. All right, let's keep pushing on here. And now look what happened. Now, look, it was at level 3, and now it dropped back down to level 1, and you can see that going from level 3 down to level 1. When it did that, guess what? It gave off a marking that we have here. Okay? So, what I'm going to do, for the sake of time, I'm going to kick the speed up, and we're going to let this thing go. But what are you noticing? Well, you're noticing that the electron is getting hit. It's getting these energy packets, and as you notice on this side, you notice it's going up and down and up and down and up and down. Now here's the thing. Does it always, if you notice, does it always go down to, from wherever level it is, down to level 1? No. No, it does not. Okay? How do we know this? Well, we know this because if you look at these colors here, they're telling us that the electron doesn't crash all the way. The bigger the crash, the more energy you're going to get being released. And ultraviolet, for what we're doing here, has the biggest amount of energy, which tells us that is the greatest fall. Whereas when you're talking about a little drop here, then you're going on the infrared side because that has the less energy because it's got a longer wavelength. Okay? Here, look at the UV. It's got shorter wavelength, more energy. Because ultraviolet contains more energy. What do you get sunburned with? Ultraviolet radiation or the infrared? The ultraviolet radiation. Yeah, absolutely. So now you're seeing what's going on here. You're seeing how things are changing. You're seeing now these are the emission lines that I was trying to tell you about in those fingerprints of light. That's it. That's what it is. And that's the clue that tells us the electrons are giving off this energy. Okay? They're telling us that it's giving off this energy, and that's what we have going for us. Okay. I'm going to switch a bit. I'm going to go back to here, and we're going to leave that simulation alone. We're going to let it run for a while on its own. Okay, so now we have this. I've tried to show you guys what you're seeing here. Here is the electron dropping down levels from level 1 to whatever level it is here in this illustration, and as it does, it gives off these lines. That's the key thing, and we got that other one right over here. It's the same idea. When it gives off, when it drops those energy levels, it's giving off that energy. That's what we pick up. Okay? Now, what does that look like on here? Well, if we went ahead and slowed this down, look, see how this thing is going down like this? It's not going, oh, here's another one going down like this. If you notice, the photons of light are going up this way. But when you see it going, oh, see, there's another one. Those are the ones that tell us the clue. Those are the energy that the electron gives off when it's dropping. Really, really going. Now, I'm going to set this thing back up to fast. We're going to go back into the notes here, and we're going to move on. So every element has their own emission spectrum, their own fingerprint of light. Now, some of the lines are grouped really, really close together, and some of them are grouped really, really far apart. Well, wait a minute. What do you mean when they're close together and far apart? Well, if I look here, and I see lines like this, and I see these different lines, these lines here, they're close together. Guess what? Same level, but different sub-levels in there. Ooh. This is a separate level from this. This is a separate level from this one. It's also a separate level from this one. So maybe this is level 1, level 2, level 3. And all these are level 3. It could be 3S, 3P, 3D, for example. Okay? So that's what we're talking about when we look at the gaps between the lines. When you see these lines close like this, same level, different sub-levels in there. Here, when you look at this, it is 2 different levels. Just like here, 2 different levels. And if you look at these 2 lines here, again, it's another level that's there. Okay? This is the proof, guys, that sub-levels actually exist. And they came up with the sub-levels of S, P, D, and F, and that was based on the shape that the electrons seem to be doing when they create all of this. So, what in the world does that look like? Well, what you end up seeing is that these levels fill up with electrons in a certain particular order. Okay, the lowest energy levels always fill first. Now, if right here where my hand is, that's the nucleus of the atom, okay, then these are the levels above the nucleus of the atom, which, interestingly enough, kind of coincides to what we've got here. Here's level 1, level 2, level 3, 4, 5, and 6. Okay, so if you look at it, here's level 1. There's only sublevel S, 1S. That's it. Okay? Well, what's the shape of the S? Well, it's the shape of a sphere. Okay? That's the idea. All right, so now the higher you go, the more energy is involved with it. Now electrons, when they go up, they're going to come down. They can't stay up forever. It's when they come down they give off the energy. So when we look at the electron distribution in the atom, okay, the S sublevel holds 2 electrons at the most. The P sublevel will hold 6 electrons. Now there's 3 orbitals in that sublevel. The D sublevel has 5 of these orbitals, if you will. Each one, they make up the sublevels, okay? And you may remember we did a sheet where you had electrons that you put in the box and you put in an arrow. One arrow going up and one arrow going down. Well, remember that the electrons have to spin opposite of each other in order to stay stable. That's the idea. Heisenberg uncertainty principle, really simple idea. We can't predict where the electron is going to be and how much energy it's going to have. That's a huge thing because his discovery led to the development, ultimately, of this model, along with the other dude named Schrodinger. Okay? Now, if you notice, look how our emission spectrum is coming. See, we all got plenty of this, but you notice now how these lines are forming. Now remember, this is based off of one hydrogen atom. But in reality, when we look at something like this in the real world, we're not talking about one hydrogen atom. We're talking about lots and lots of them being at different stages. These electrons being at different stages of excitement and all that. Okay, let's move on here. Okay, I couldn't resist. All right. So what is it that these orbitals look like? Well, they do have these particular shapes. That's true. Okay, and I'll let you guys work on that. You've seen that with the simulation that you had. We have the Aufbau and Pauli principle. Okay, electrons in the atom will always occupy the lowest available orbitals. So if we look at 1s and 2s, okay, and 2p, okay, you're never going to see something like this. You're never going to see where 1s is empty and the 2s is full and the 2p is kind of sort of full. You're never going to see that. This has to be filled according to Aufbau. Aufbau says you've got to fill the lowest. Why? That answer, stability. Now Pauli said in a maximum number of electrons in a sublevel like this, it's 2. And I know I've used the word orbital and sublevel. They pretty much mean the same thing. Okay, it's an area where the electrons hang out in. But the maximum you can get in a sublevel is 2, and they have to spin in opposite directions. Okay, and that's the general idea when I had you guys do the thing with the fingers. And I had you guys spin the fingers in opposite ways. Okay, I have to pay attention to my timing. Okay. This I am going to have to do for a second part, okay? And at that point, ladies and gentlemen, I'm hoping that this will make a little bit more sense to you. What we're seeing here, we're getting these readings. These readings about, excuse me, these readings are electrons giving off the energy as they're coming down from their hyper. Where are they getting the energy from? The photons of light that come through. That's what it is, ladies and gentlemen. And how are we picking it up? Because those energy releases, they get released off to the sides, and we're able to pick that up. And this, ladies and gentlemen, is our fingerprint of light. I'm hoping that this made a little bit more sense for you guys. Stay tuned, there is a part 2.